So one of the most famous experiments in all of physics is the so-called Young's double slit experiment. And in this experiment, we passed light through these two tiny little holes and shown it onto a screen at some distance away from it. Now what we had and what we saw from this was that light would form a nice bright central peak, and then a dark spot, and then a slightly less bright spot, and then another slightly less bright spot. So we had a kind of pattern here on the back of the screen where there was a whole lot of light in the middle, and then a dark spot. And then there'd be a whole lot of light, though not quite as much as the central spot, and then another dark spot. And this came to be known as an interference pattern. Now, this interference pattern is caused by light combining together. So at some points, we have two waves of light from the upper and the lower slit. And each of these waves has its own separate shape, separate wave-like structure. And at some points, the peak of one wave would match with the peak of another wave. And at these two peaks, you'd get a central bright spot. So the bright spots are where these two light pieces, these two waves coming from these two slits interact and combine. And then at some points, there's maybe the bottom of one wave interacting with the top of the other wave from the other slit. And at these points, you get these so-called dark spots. And we can describe all of this physics by assuming that light is actually a little bit complicated. That light is a combination of particles and waves. So light has a dual nature. Light is both a particle and a wave. And we can mathematically describe this with the interference equation. And the interference equation tells us that m times lambda equals d times sine of theta, where m is equal to 0, plus or minus 1, plus or minus 2, and so on. Now, what do all of these things mean, and what are all these variables representing? So let's draw a Young's double slit again. And we'll draw a screen. And we'll imagine that we have waves coming through. So we have a wave coming through the top, and let's make that a red wave comes through. And then we have waves coming through from the bottom, and the wave coming through from the bottom, and they hit on this back screen. And they hit at this point, and they combine. They combine together to form a central bright spot. So anytime you're getting these two waves combining together and striking this back screen, we get a bright spot, and we'll call that bright spot, that first bright spot, m equals 0. This is known as the order of your bright spot. And then we can have the top wave goes through and hits the back screen, and we can have the bottom wave go through, and it will hit the back screen as well. Except this bottom wave has to travel a little bit further because it's a little bit further down. So these two waves, they're going to combine, and they're going to give us a bright spot here, and that will be the m equals 1 bright spot. Or we could have the case where the green wave doesn't travel as far, but the red wave does have to travel farther. And that's going to be another bright spot. So it's the same as the top bright spot, except the red wave is traveling further this time. And this is going to be the bright spot m equals -1. Then we could form another bright spot. We could have another bright spot of the red wave coming up and hitting a little bit higher up, and we can have the green wave traveling just a little bit further to form this m equals 2 order bright spot. Or conversely, we can have the red wave traveling a little bit further to reach the wall, and we can have the green wave traveling a little bit less far, and these two waves combined, the peaks combined with the peaks at these points on the walls, and we get the m equals -2 bright spot. So we should have a good understanding now of what this m represents. It represents the order of your bright spot. Now, what do these other things represent? Well, lambda represents the wavelength. Lambda is how long your wave is. So that's pretty self-explanatory, and we've talked about wavelengths already. So next, to understand D, we kind of have to redraw this Young's double slit experiment. So let's get rid of all these light rays that we had, and we're going to take only 2 light rays to actually draw and form a bright spot. And we're going to see what D represents. So I'm going to have, again, my red line that comes up and forms this bright spot m equals 1. And then I'm going to draw the green line coming up and striking the screen. Okay. Now to figure out what this D is, the D is actually the separation between the slits. So it's this line right here that separates the slits. It's the size of the slit. So D is equal to the slit width. And then sine of theta actually represents something in this, this picture that we've drawn. What we can do, and because we love right triangles in physics, we're going to form a right triangle. So I'm going to drop a perpendicular line down here. And we can see that this forms a nice right triangle. I have a line going down, I have this green line, and I have this blue line, forming this nice right triangle. The hypotenuse here is D. So where does this sine theta come into play? Well, theta is going to be the angle up here at the top of this triangle. And that line theta comes from doing some trigonometry. We can imagine that that theta is also, if I draw a line that goes completely horizontal from the double slits back to the screen, and I can do that from either one of these lines. That is the path of the line, path of the wave, to forming the bright spot. That angle is theta as well. So all of these are thetas. And we could do lots and lots of trigonometry to see this, but the important part is that that gives us this wonderful right triangle here. And the important thing to note is that this piece of green, this line that's green right here, that is actually the same exact length as this piece of red. But then this green line, this one right here, this wave that's traveling from the bottom slit has to travel a little bit further. It has to travel also this little piece along this right triangle, along this little yellow right triangle. It's got to travel that little bit extra to get to the point where it's going to interfere and combine with my other wave from the red wave that's traveling from the upper slit. So I need to know what that distance is. That distance from the slit to the point where I get to the point on the green line that makes it the same length as the red line, the same distance that the top wave travels from the top slit, I need to know what that distance is. That distance we should be able to see. If we write it down, we can denote it with the letter, let's call it L. And we can see that if we take sine of theta, that's equal to L divided by D, the opposite side divided by the hypotenuse. And if I solve this for L, L is equal to D times sine of theta. So L, we can call it the path difference between the light rays that travel to constructively interfere. So what does that mean? How do we actually make sense out of this using the Young's double slit actual equation, m lambda equals d sine theta? Well, then this just tells us that the path difference L is equal to m times lambda. So the amount of distance that one wave travels to reach the screen is equal to some integer multiple of wavelengths. So if I want the path difference if I want the 0th order, so this central line. At the central line, if you recall, we had the red light comes in and we had the green light comes in, and they're both going to be traveling the same length, the same distance. So this L, the path difference, the amount of distance that the green light travels relative to the red light, is going to be exactly the same. These are going to travel the same distance. So that would tell us right away, for the 0th order, m equals 0, the path difference, L, which is equal to d sine theta, is also equal to 0. In a picture form, what does this look like? What do these two waves look like if I draw them as actual waves? I've got the top wave, maybe looks something like this, and the bottom wave would look exactly the same. Same exact length. Now let's say that L, the path difference is different. Let's say I use m equals 1, and I find that first order bright spot. So what does that look like? Well, in the double slit, we have something that looks like this. We have our red light that travels some distance, and our green light is going to travel further. It's got to travel this extra bit of distance right here. So what is that distance? Well, I can find that from m is equal to 1. So I use m lambda equals d sine theta. M lambda equals L, the path difference, which is d sine theta. Plug in your 1, so you get lambda equals the path difference. So the green wave has to travel one further wavelength. What does that look like? Let's draw what these wavelengths might represent. So I might have the red wave travels again, looks something like this, a wave that goes up, comes down, and then goes back to its regular position. The green wave, however, is going to have a path difference. It's going to have a length L that's a full wavelength longer. So it's going to travel one wavelength, and then it's going to travel another full wavelength to make up that extra distance right there. So this clearly isn't drawn to scale, but that extra bit of distance that you see is this extra bit right there at the end. So it's got to travel a little bit further. So that's where Young's double slit equation comes into play. That's where everything comes from. M lambda equals d sine theta, where m is the order of your bright spot, and you can have a central bright spot that'd be equal to 0, or corresponding bright spots on either end, plus or minus 1, plus or minus 2, etc. Lambda is the wavelength of your light. D is the slit separation, how far apart your slits are. And theta is the angle between your light ray going to form your bright spot and a parallel line, a parallel horizontal line that goes to the screen. Now, what does this look like for dark spots? Now, for interference of dark spots, we can predict those as well. So there's our screen. I have my two light rays that meet and form a bright spot. But then next to that bright spot, I can have a light ray that comes straight in and then I can have a light ray that comes from the bottom that's actually going to destructively interfere. And I can use the exact same equation, exact same concept that we just talked about, except what I want here is the red wave, maybe I have it travels and looks something like this. So I would want the green wave to form a dark spot to travel slightly different distances. So I want to make sure that it hits the back of the screen so that the wave looks something like this. So that I have the trough of one wave, the bottom of one wave, intersecting at the screen with the top of another wave. So what I do is I look at this picture, this kind of wavelength drawn picture, and I look at what's the path difference here. How much longer is this wave so that I can make them actually cancel out and form a dark spot so that the top of one wave hits the bottom of another wave. That means the light will cancel out. And if I look at this and analyze these wavelength differences, I can see that this is actually equal to 1/2 of a wavelength. So this gives us an equation that we can use to kind of adapt our Young's double slit equation to give us dark spots, to get destructive interference. So I no longer want to be a full wavelength change. I want a half a wavelength change. If I do m plus 1/2 times lambda equals this path difference, this d sine theta, then I will get destructive interference, and I'll find dark spots. And the m's here, again, are going to be the exact same. M equals 0, plus or minus 1, plus or minus 2, and so on and so forth. So I can get dark spots, or I can get bright spots in interference using all of this mathematics, using this algebra and trigonometry, and this concept of path differences.